Good morning, all of you. Camera
लाईव्ह आहे तो त्यांना लिहितो त्यांना आपण सर इथे येऊन बोलू शकतो.
हा सर इकडे बोलून घ्या कारण कॅमेरा दिसलं पाहिजे. कॅमेरा इकडे फोन कर. हा मागे 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 कॅमेराकडे.
Good morning, all of you. I welcome our today's guest, Dr. Smita Dani. Madam is joining us from California, and let me introduce her to all of you. Madam holds a PhD degree in electrical engineering from University of Colorado Boulder. Her research was focused on high efficiency gallium nitride based power amplifiers and transmitters. Madam has worked in various reputed international companies like National Instruments, Infineon Technologies. She has worked in various aspects of RF design. She has worked on starting from component designing like power amplifier. She has also worked on system designing like radar system. Madam is skilled in variety of engineering tools and techniques, including RF and microwave simulation software, PCB design, and hardware testing. So she continues to work on advancing RF and millimeter wave technologies in areas like communication, defense, and aerospace. So we are having very highly skilled and technical person to deliver a talk for today's session. So I welcome Dr. Smita Dani, madam, and I request her to please start with her session.
Thank you so much. Can you hear me?
Yes, ma'am. Yes, ma'am.
Can you hear me? Okay, thank you. 1 minute. Let me share my screen. Can you see my screen?
Yes, madam.
Okay. It would be better if you mute on your end, otherwise there will be lot of echo. So, जर कोणाला questions विचारायचे असतील तर they can just maybe raise their hand or put it in the chat. So I can start, right? Can I start?
Yes, madam.
Yes, ma'am.
Okay. Okay, thank you so much for having me. So today I'm giving a talk on fundamentals of RFIC and MMIC design. So I will be going through these topics today. So first will be introduction to the topic itself and what are the applications. Then we will talk about the actual technology, fabrication and design considerations. And then we will dive into some actual active circuit design considerations as well. So let's first start with myself. So I am originally from Mumbai and I finished my bachelor's from University of Mumbai. And then I moved to US to pursue my PhD in RF and microwave engineering back in 2008. And then I have been working here for the past 11 years in the industry. So I have worked in both big companies and startups with applications. This year I started a company in India. My company's name is Milliwave Technology. And I'm building the company to basically focus on millimeter wave integrated circuits for applications in defense, aerospace, and 6G communications. So let's first start with what are RFICs and MMICs. So when we talk about RFIC, it's defined as radio frequency integrated circuit, and MMIC is defined as monolithic microwave integrated circuits. So both are kind of similar. There is subtle differences between the two. So an RFIC is a compact semiconductor device which is designed to process and transmit RF signals. RF signals are signals which are ranging from about 300 megahertz to 3 gigahertz. Typically, these are used in wireless communication systems such as smartphones and Wi-Fi. Monolithic microwave integrated circuit is also known as a MMIC. It's a high-frequency semiconductor device which integrates multiple microwave components on the same chip. So microwave meaning frequencies going from 3 gigahertz to 30 gigahertz. These are microwave frequencies. And these are commonly used in radar, satellite, and some millimeter wave applications as well. So what are the basic differences? As you can see in frequency range, I mentioned RFIC goes up to 3 gigahertz. MMICs go from 3 gigahertz all the way up to 300 gigahertz. Now, if you look at RFIC, mainly the materials used are CMOS or silicon germanium, which are lower cost materials. For MMICs, we use more high-end, high-power materials such as gallium arsenide, gallium nitride, or even indium phosphide. CMOS is which integrates multiple metal layers as well. So these can range anywhere from like 7 layers all the way up to 50 layers also. In terms of applications, RFICs today have huge amount of application in telecom sector, specifically mobile phones, Wi-Fi, Bluetooth, consumer electronics. MMICs are more geared towards defense applications such as radar or satellite communications, defense, aerospace systems, etc., where the performance based on size, weight, and power is more appreciated as compared to the cost. Integration-wise, RFICs, we are able to integrate both analog, digital baseband circuitry onto one chipset. MMICs are pertaining to integrating analog circuits such as amplifiers, mixers, oscillators, etc. In terms of cost, RFICs are very cheap because it's CMOS. MMICs are higher cost due to the materials being used. In terms of power handling, MMICs are able to handle much larger power based on the materials that are being used. And then in terms of package sizing, MMICs have a slightly larger package as compared to RFIC. RFIC, since we have a lot more metal layers, there is vertical integration possible, and this makes the package extremely compact. If you look at the performance, we see that it is optimized for RFICs to perform at low to moderate frequencies with moderate and low power levels. MMICs are designed to perform for higher frequencies with higher power levels. So why are these circuits compact, right? So if we compare a PCB technology such as Rogers FR4 with RFICs or MMICs, we find that RFICs and MMICs are 10 times smaller than the PCB. So the reason for that is the dielectric constant of the material which is being used for integrating your passive and active components in RFICs is very high. So if you are talking about like silicon, gallium arsenide, gallium nitride, they have very high dielectric constant. So when the dielectric constant is very high, the wavelength becomes very, very small in that medium. And that is the reason why all your dimensions scale down into micron levels versus millimeter level for RF frequencies. And if we consider like the capacitance, which is given by epsilon naught epsilon r A over D, we see that since the epsilon r value is much higher, we are able to achieve much larger capacitance values with a very small footprint in RFICs or MMICs as well. So if we go step by step, first is integration of active and passive components together. If we consider like a PCB technology, we will see that all the components will be separately soldered onto the PCB. So if it's like resistors, capacitors, inductors, you will buy separate parts and you will solder them on, and then your transistor, etc. Whereas in RFIC or MMIC, everything is on the same substrate. It is designed on the same substrate. So there is no separate part that is integrated. Everything is together. So that's why the size is very compact. Of course, we have shorter wavelengths. As I mentioned, that the dielectric constant is very high, so the dimensions are much smaller. And this also results in reduced parasitics and interconnect lengths as well. Also, we are working with advanced semiconductor processes, which are working with submicron and deep submicron lithography. So, which this enables like very small feature sizes in nanometer range. And this allows for packing of many different RF functions into a single die. So if you have like a transceiver front end, you can have the PA, LNA, mixer, everything on a same IC as well. So what this does is it eliminates packaging constraints. So we are not dealing now with discrete package footprints everywhere, but we just will have like one package and in which the IC will be integrated, and it can be like flip chip or wafer level packaging further to shrink the circuit dimensions. If we look at one second. So you can see my slides clearly, right? Hello?
Yes, ma'am.
Yeah, you can see clearly. Okay. Okay. So if we do a wavelength comparison, we see that as compared to S-band, C-band, X-band, we see that free space wavelength is much larger as compared to substrate materials such as Rogers, FR4, etc. And as we move to higher dielectrics, we see that wavelength reduces much more. So we are going from like 37.5 millimeter, we are going down all the way up to 10 millimeters. So it's a big scale in terms of your wavelength. And this is the reason why these circuits are very, very miniaturized and compact. So what is the importance of these RFICs and MMICs in modern technology? So we can see here that there is a full spectrum shown which goes from UHF all the way up to millimeter wave band of 300 gigahertz. And we can see the entire electromagnetic spectrum. What are the different applications? So we see that like for RF frequency, our older cell phone standards such as 2G, 3G, 4G, they all used RF frequency along with GPS, cable TV, modem, RFID tags, wireless LAN access points, etc. Then in the microwave frequency range, which is the modern communication systems, we have more advanced 5G standards. Then we have point-to-point links, satellite comms, etc. Also imaging, And then if we go to millimeter wave, we have more advanced driver assist systems, automotive radars, military radars, etc., and scientific imaging applications as well. So if we look at it from a perspective of where which technology can be used, we see that there are multiple segments. So there is like consumer electronics, there's communication systems, there's automotive, there's also healthcare. So even in healthcare systems, all these chipsets are required. And if we see in terms of the current 5G and 6G standards, we see that a lot of communication is happening in wireless domain, and there's going to be a lot more done through satellite communication. So we are already see that Starlink Star satellite constellation is providing very high quality internet to remote areas across the planet. So these kind of internet systems are going to come more and more into picture. We also have Internet of Things, where all our different kinds of devices, such as home alarm systems, or doorbell systems, or even irrigation systems, they are all connected wirelessly as well. So all these systems are going to be requiring more and more utilization of these chipsets. If we look into defense and aerospace, we can see, like for example, this is a phased array system, and this is a automatic electronic scanning array. So in this array, it's basically a phased array antenna, which has all these electronics hooked up behind it in order to control the beam. And the RF segment of that antenna consists of high power amplifier chipsets and low noise amplifier chipsets, along with other mimic circuitry as well, to enable the transmit and receive function on the phased arrays. So this is a high power system. So it's like a military radar. So this is also a big application for these chipsets. The main advantages being that we have miniaturization, yielding to high performance. We have reliability, because the chipsets are manufactured on wafer, so the processes are much more reliable, and it's also cost-effective production once it is reaching high volume. So if we compare like traditional discrete circuits versus RFICs and MICs, we see that in terms of size, of course, RFICs and MICs are much more compact compared to discrete circuits. Weight-wise, they are more lightweight because of monolithic integration. There is much less additional packaging, so it's much easier for the system to hold these chipsets. In terms of performance, RFICs and MMICs are much higher performing at high frequencies, and it also has more reliable performance because fewer interconnections. But in terms of cost, we see that only when it reaches high volume, it's more cost effective as compared to low volume. And other things we can look is like ease of fabrication. It's a single step fabrication process. And in terms of applications, it's essential for modern communication system, whereas discrete circuits are limited to low frequency legacy systems. Now, if we consider 6G applications, we are also looking at like smart city applications, not just IoT, and we are also looking at quantum computers as well. These are also potential applications where you will see the utilization of these chipsets. So if you are interested in the IC world, there are a lot of different areas of engineering you can work in. So if you look at an RFIC or MMIC design process, there are multiple types of engineers that work to make the entire process successful. So one is the semiconductor process engineer. This person will like work on the actual semiconductor physics and improving the physical process by itself. The second is device model engineering. So once you have your process defined properly, then the device modeling team essentially takes the parameters from that semiconductor process and develops a model, which can then be used by a circuit designer to design circuits, and that's the RFIC design engineer. And then once the circuit is designed, then there is package development engineering to develop a proper package in which the IC can be secured and integrated into the system. And then there's system integration engineering as well. So there are different aspects of IC design, and it's a very interesting field to be in. There are multiple applications as well, along with different kinds of roles. Okay. So next, let's move on to the details of each application. So if we look at the evolution of 5G standards, we see that compared to 4G, in 5G, the latency is much lower. So if we compare the latency versus the data traffic, we see that 5G is much more superior as compared to 4G standards. And this is the reason because everybody wants just more and more data. So everybody consumes so much more data that the 5G communication standards define on terms of higher data rates or data throughput. So in order to do that, the frequency of operation also has to move up in order to accommodate a lot more spectrum. So the available spectrum for 4G standards was much less as compared to the spectrum available for 5G. So for 5G, we are moving up to 30 gigahertz. So there is a lot more spectrum availability as well. And this has made the applications for MMICs much more prevalent. Now, if we consider a base station, this is a base station that is shown over here. And we see that for 5G standards, there are multiple zones. So if you are at like lower band of the standards, your transmit power is much larger because the free space path loss is much less. Whereas for higher bands such as 28 gigahertz, the zones are much smaller. So there are a lot more base stations placed for these frequencies. And then if we look at the phone, our phone as well, if we look at the interior of the phone, we see that there is a lot more integration today, not only for 3G, 4G systems, which already exist, but also for millimeter wave 5G systems as well. So there are separate antenna integrations as well. So we can see that it is a very challenging job to do integration of these chipsets within a system, and that makes this field even more interesting. Now, if we look at like the 5G multi-user front-end architecture, the ultimate goal is to not have like a single beam of data transmission, but have like user-specific beams targeted to specific users or devices. So in order to do that, the 5G antenna array foundation is more of a phased array radar with multiple beams being transmitted. And if you look at the front end of this phased array, we say that we have power amplifiers, phase shifters, attenuators per element, and the same goes for receives chain as well. So this requires high level of integration since we want per element a single chipset to be designed. So now here if we look at this front-end module, this is a 26 gigahertz 5G front-end module. So here we see that we have a power amplifier and the interface of the amplifier is over here. And then we see that it's wire bonded to the power amplifier IC. Then you have a harmonic filter, and then you have a switch. So this switch basically toggles between transmit and receive function. And then this is a receive chain, so you have an LNA again going through some couple line filters, etc., towards the exterior interface, which will go into the system. So this is an example, and this is like a very high substrate, alumina substrate, so it's very compact, and this can then be integrated onto the phase array. Now, as I mentioned, the future of telecommunication, which is moving more towards 6G applications, we are also talking about working in the terahertz range as well. And there is applications in holography, then there is applications in virtual reality as well, and sensing, of course. So we see that by 2040, we are going to have the spectrum utilization till 1 terahertz. So there is a lot of potential applications for MIMICS. Now, if we look at radar systems, we see that compared to the old age radar systems where we had mechanically scanned beams, now we use phased array antennas. So this is able to track basically multiple aircrafts simultaneously because it does not have physical rotation on it, but it is able to send out multiple beams in multiple directions. So this is a big system which is very useful in commercial and defense applications that requires these front-end chipsets. Now, these radars are electronically scanning radars, meaning that the beam is electronically controlled and there is no physical rotor attached to the antenna. So since it is electronically controlled, all the integrations of phase shifters which enable this kind of beam steering application, everything has to be integrated. And here we see that the front end of the TR module for each of the element on the phased array consists of a controller, then it has a CMOS digital circuitry, and then it has an analog either GAN or gas circuitry going towards the front end. So it has multiple chipsets integrated onto the system as well. In terms of like the advantages of this radar versus older age radar is you definitely have faster beam steering and the resolution and sensitivity is also very high. And there is low probability of any interception and it is also highly resistant to jam. Now, what is the role of RFIC MMIC in this technology is since we are looking at higher frequencies to operate this radar in, we use this technology to design the circuitry and also make it very much compact and lightweight as well due to the miniaturization and integration. And if we use gallium nitride based mimics, then it can handle a lot of power and it's also more efficient in terms of energy. So this is the application in radars, and then in aerospace also there are a lot of applications for mimics, and I have listed them down here. I don't need to go through it one by one, but you can go through it once you have access to the slide. But especially in SATCOM, there is high-level applications of LMAs and PAs. So, like for example, this is a gas mimic with a very low noise figure at X-band, and then this is also a Ka line power amplifier, which is 10 watt gallium nitride. Okay. So next, we will move on to the actual technology. But I just need 2 minutes. I just need to drink some water. So I'll be back.
Okay.
Okay. So next, let's talk about the actual substrate technologies. So if we consider the technologies versus their power handling, so we see in this graph that CMOS silicon germanium has lower power density, lower power handling capability, but it is able to go quite high in frequency. Gallium arsenide can handle like medium amounts of power, 1 to 10 watts of power, and it can also go higher in frequency. But of course, each technology, as you scale up in frequency because of the device parasitics itself, the power, output power, everything starts dropping significantly. If we consider like LDMOS technology or silicon carbide, we see that it is able to have lot more higher power, but it is limited to very lower RF frequencies. Gallium nitride is very powerful, and it is also able to scale at higher frequency. Indium phosphide scales very well in terms of frequency, but it is having low output power as well. So these are the different kinds of technologies you would use for a RFIC or MMIC circuit. So now let's look at the overview. So if we look at like the MIMIC development timeline, we see that the first method for growing single crystals was started in 1916, and by 1947 Bell Labs invented the transistor. And then in 1959, first patent of a germanium integrated circuit was filed. And in 1961, the silicon IC was patented by Fairchild Semiconductor. Slowly, the process evolved, and first, like silicon MIMIC was developed, but with very high loss. Then, a method to actually develop gallium arsenide FETs was discovered, and then that started transforming into the first MMIC circuit in gallium arsenide process around 1968 to 1970. And then in 1976, the first MIMIC using a gas FET was reported. So there's a long history behind this development, and it has since been evolving. But this is like one of the world's first gas FETs, and it was a very simple like interdigital capacitor, a one loop inductor, and then the FET itself. After that, we see that the actual commercial process started getting launched around 1996 for a 0.2 millimeter gas FET process. So now let's try to understand the basics of the transistor used in the MMIC or RFIC. So we are looking at a field effect transistor. So field effect transistor is typically a transistor that controls the flow of current using an electric field. And it's a 3-terminal device. So it consists of gate, drain, and source. So the gate essentially controls the flow of the current by applying a specific voltage. Drain is where the terminal has output current, and the source is the terminal where the current enters. So if we look at like the cross-sectional view of a transistor, we have the gate terminal, we have drain, and we have source, and then we have this channel over here. Okay, so when our channel is pinched off, meaning that our gate voltage is below pinch off levels, we see that, or at pinch off rather, that the gate is the channel is cut off. So it's still closed. So there's no electron movement going from this end to this end. Then once you start increasing that gate bias above the pinch off voltage, the gate channel starts opening up, and we see electrons flow and current starts increasing slowly. So if we look at like the top view, we see that this is how we define the FET and the current direction for the FET. So now if we look into like the details of how it actually works, we see that VDS when it's positive voltage and when VGS is negative voltage, we see that at this interface, which is N channel and P channel, we have electrons being repelled, and they start combining with the holes in the P channel substrate. Now, when the VGS is actually at zero potential, you have current flowing through the MOSFET. But when you start reducing the gate voltage, the electrons start repelling and the channel gets closed. So we see that on this IV curve, we see that negative voltage at pinch off, the current is zero. And then as you go increase the gate voltage, your current is flowing fully. So if we look at the FET geometry, usually in mimics, we define it in terms of gate width, right? So the length of the gate is actually fixed, and the gate length is defined by this dimension shown over here. So gates have multiple fingers. So for example, here it has like 4 fingers, and each finger's gate length is defined by this minimum dimension here. So if we say that it's a 0.1 micron process, that means 0.1 is the gate length, that is the minimum dimension available. And gate width is the total width here, that is the vertical dimension that I'm talking about, which encloses the entire channel. So typically for max gate width, if we say like for S band, we don't use more than like 150 micron. And then for as we go up and up in frequency, the gate widths also start reducing because the parasitic starts increasing. So for gate length, it's the shorter dimension of the gate, and this controls frequency response. So if the gate length is smaller, your FT and Fmax is much higher. FT and Fmax being the frequencies at which your power gain and current gain is 0. And gate width is the longer dimension of the gate, and this determines the power capability. So wider gate width will have higher DC and RF current, but it will also have worse performance at higher frequencies. So what is the total gate periphery? It's the number of gate fingers times the unit gate width. So if my number of gate fingers is 6 and unit gate width is 100 microns, my total gate periphery is 600 microns. So if we compare silicon and heterogeneous technologies such as gas, indium phosphide GaN, we see that in terms of the band gap energy, silicon is lower, whereas gallium nitride is much higher. And that's why gallium nitride is able to handle a lot more power. So what is band gap energy? Band gap energy is the energy required by the electrons to move from valence band to conduction band. So since GaN requires much larger energy, it's able to handle a lot more power as well. And there are other like physical differences between the two technologies. But if we consider mainly like the breakdown field, we see that that is also much higher for GaN. So what makes the heterogeneous semiconductors different? They have something which is defined as a pseudomorphic junction. So a pseudomorphic junction is basically a junction of material that is designed in order to achieve a lot more band gap energy. Okay, so if we consider like the semiconductor growth, then we have a substrate on which there is a stretched to match lattice of materials which are causing these pseudomorphic junctions. So if we look at the band gap energy versus lattice constants, we see that the semiconductor materials such as AL-GaN or AL-gas, IN-GaN, all these are different semiconductors which are combined together in order to have a pseudomorphic junction whose band gap energy is much higher. So that is called the 2D electron gas layer. So for gallium nitride, if your substrate, so gallium nitride doesn't exist by itself. It has to be grown on top of silicon carbide or silicon. Since it's extremely expensive material, so it's never like kept as a substrate by itself. But you grow a GaN and GaN 2D electron gas layer, which enables the material to have much larger band gap energy. So what are the positives of this? Positives are there is reduced scattering of electrons, there is higher current density and lower on-state resistance as well. This also has much higher breakdown voltage and much reduced parasitic capacitance. So this helps in improving the performance of the transistor. So if you look at the actual fabrication process of these semiconductor materials, here I have laid down the actual process, how the semiconductor material is grown into a full-scale unit. So first the first step is to of course do a proper substrate selection. So whether you are doing a silicon carbide or gas, sapphire, silicon, whatever base material you have. And then on top of that, you have to do an epitaxial growth using molecular vapor deposition of the buffer channel and barrier layers. So channel meaning the actual 2D electron gas layer and the channel layer through which the current is going to flow. Then we do MESA etching for device isolation, since we do not want, we need to have source, drain, gate separated from each other. So we need to have the device isolated from the surrounding. Then we do ohmic contact formation. This is to contact metal deposition on source and drain, so that we can interface it with the outside world. We also put then a passivation layer, and this passivation layer a lot of times forms capacitors on the substrate as well. And then we do the gate fabrication. Once that is done, we will do the interconnect and final processing. So here I have shown the process in detail. So first you have growing of substrate and the epi layer. And then the epi layer itself consists of like the cap layer, which is either GaN or silicon nitride. Then you have the barrier layer, which is AlGaN. Then you again have the actual channel layer, and then you have the buffer layer below it, and then below it you have the substrate. So it consists of multiple layers and the epi layer. And as you can see here, you have the ohmic contact layer, then you passivate, then you add gate, then you add metal passivations, then backside thinning, and then BTRs going to the bottom as well. So if we consider the different types of lithography, we have etch process versus lift-off process. So there are advantages and disadvantages of these processes. And if we consider like, etch process, in etch process, metal is pre-deposited on the wafer, and photoresist covers areas where metal should remain, and unprotected metal is then removed through an etcher using chemical etching. And this is suitable for thicker layers because there might be some undercutting that happens. Whereas in the lift-off process, a photoresistant is applied first, and the metal is deposited in a thin layer, and then resist is dissolved, lifting off the excess metal. So this produces sharp edges, but then it's not ideal for thin layers. So these are the kind of different processes that can be utilized by the process engineer to make sure that the device fabrication happens in a very precise manner. So here we can talk about like resolution limit. So what is the minimum feature size? It depends on like the UV wavelength, and it also depends on the lithography. So what kind of lithography you are able to achieve, that will determine what is the resolution limit. So if you consider like gallium nitride or gallium arsenide, you will see different processes. You will see 0.25 micron process, 0.15 micron process. So basically what they have done is they have improved their lithography process in order to achieve much smaller dimensions. So that has enabled them to work at much higher frequencies. So here the entire mimic process has been shown in very much detailed review. So we see that this is like a MESFET or a HEMT process. On top of that, you have like silicon nitride passivation. Then you have through gas layers, and then backside metallization as well. So when we talk about like creation of passive components, we are talking about like capacitors, which are called min caps. Min cap stands for metal insulator metal capacitor. Then you have resistors, and you have inductors as well. So when we talk about doing a device isolation, devices with contacts to the active layer must be isolated to prevent unintended connections. So isolation is achieved either through MESA isolation or ion implantation. So what is MESA isolation? Here the active areas are protected with some sort of photoresist and the surrounding material is just etched away. So what it results in MESA-shaped raised areas on the semiconductors. Whereas ion implantation is a technique where high energy ions are implanted to disrupt the crystal structure and rendering areas as non-conductive. So this helps the active device get disconnected from the surrounding areas as well. So here, this is an example of the structure. So we can see in this figure over here, this spiral is shown as an inductor on a single metal layer. And we see that this one is a first interconnect layer. It's an underbridge that is then connected through a via, interlayer via, to the second top layer, which is a spiral inductor. And then this is a MESA resistor. So you have metal, metal, and the resistive material. And then this is a MIM capacitor over here. So we can see here this is a transistor. So it has two gates. Okay, and then you have the first interconnect metal joining the gates, and then output to the drain. So in terms of the design process, now that we know, okay, this is the actual mimic process, this is how the mimic is like passive and active structures are formed during fabrication, then as an engineering designer for a mimic, what should we do? So for that, you basically get something called a process design kit. This is a design kit which is given to you by the fabrication house. So for example, if you are getting your devices fabbed at Bin Semiconductor, then you have to ask them for a process design kit. And what this process design kit has is it has all the models of their active and passive structures, which you can use to do your design. So in the mimic design process, you basically define the requirements, structural schemes development, then electrical schemes development, and then you basically start doing the design and modeling of passive elements, then integration with active elements, full topology design, verification, and then you produce the photo mask files, and then you send it to production. So in terms of layout, how do we go about like the mimic layout? Is first we design a circuit with ideal components, and then we swap in the foundry component. So what does this mean? This means that initially, if I have to, let's say, design a low pass filter, I will just use an ideal LC value and I will design the filter. And then I will swap in the L and C with the foundry process parameters. So if I'm using a min cap, then I will add the model of the min cap and a spiral inductor for my LC model. So I will see that the performance is changing, and then based on that, I will generate my layout. Then based on like the layout constraint, I would have to reposition my components sometimes to remove any overlaps or not, like if I'm violating any design rules. Once I do that, I will again re-optimize my RF performance, again regenerate the layout, right? And then I will add my interface pads as well. And every time I add something to the layout, I will go back and check my RF response. And if it's not ideal, I will optimize it again. So this is a back and forth process that happens when you are doing a mimic design. And it is very important to do this because you don't have the flexibility to tune the circuit once you have it in your hand. If we look at like yield and engagement, then we see that in terms of the yield, we see that as my chip has more and more complexity, then my yield becomes lower and lower, and the defect density increases. Whereas if my process maturity goes up, then my yield also improves. So the defect density is dependent on my chip area if my chip area is, very large, and that can allow for defect density to be much more and process variation to be much more as well. So it's also critical to minimize the amount of area we are using as much as possible. It also helps the cost as well. Once you have your mimic in hand, then you do RF on wafer testing. So what this means is essentially you have all your circuits on the wafer and then you put probes on the wafer and test the circuit for specific RF S parameter response. So here also the testing and setup, you need probe station, RF probes and network analyzers. The challenges are that probe-to-probe contact consistency affects the accuracy. Parasitics from the probe and calibration of the probes is very important. If that is not taken into account, then the measurements can be wrong. And we have to keep in mind about repeatability as well. The advantages are that it is quite cost-effective way of screening the mimics before we package them, and this enables process tuning and design verification as well. So here I have shown how the probes basically land on your ground signal ground pads on the IC. Now your ground signal ground pads can either be then transitioning to microstrip, or they can be just in transitioning to your CPW line on the IC as well. So this is just showing the difference between a microstrip and a CPW. Okay, so next we will talk about the design considerations for passive components. So before I start this, I would like to take a 5-minute break if that's okay. Is that fine?
Yes, ma'am.
Hello?
Hello.
Okay, madam.
Okay, ma'am.
Can we take a 5-minute break?
Okay, ma'am.
Can I resume? I can resume, right?
No, ma'am, please wait. Few people are not present.
Okay. So now what all we have covered? We have covered the semiconductor technology overview. We have seen what are the basics of FET-based geometry in the semiconductor process. And then we have looked at the fabrication process itself. So now let's look into how to design passive circuits on the MMIC or RFIC. So for that, first we have to understand the RF transmission line. So an RF transmission line is an electrical transmission path designed to guide and carry high frequency signals, typically ranging from 3 kilohertz all the way up to 300 gigahertz, with minimal loss, reflection, and distortion. So since at like these frequencies, the wavelength of the wavelength at that frequency starts becoming comparable to the dimensions. We segment the transmission line into n number of small sections, which are defined by a model shown over here. So it consists of a resistor, an inductance, capacitance, and conductance. So that forms our transmission. Now, there are different kinds of transmission lines. One of the most common types of transmission lines which we use in our PCBs, etc., is microstrip line. So, a microstrip line is typically a transmission line used to guide high frequency signals in integrated circuits, and it consists of essentially a center conductor on a dielectric substrate and then a bottom metal for the ground plane. And then you can see that the magnetic field surround the center conductor and the electric field goes from the center conductor towards the ground outward this way. So for a microstrip line, its characteristic impedance and the actual loss, path loss, is dependent on the height of the substrate and the width of the transmission line. If the line is wider, then the impedance is much smaller, and if the width of the line is much thinner, then the impedance is arguably going to be much larger, right? So these are some of the mathematical equations that define the characteristic impedance of the line. How do we define characteristic impedance? Characteristic impedance is essentially the ratio of the series inductance and parallel capacitance on the transmission line if we don't consider any losses on the line. If we consider losses, then those are taken into account in calculating the characteristic impedance as well. So if there are different types of transmission lines, one is of course a microstrip, then you also have a coplanar waveguide. So in the coplanar waveguide, you have center conductor and then you have two ground planes adjacent to the conductor. So this helps mitigate the losses much more because now your fields are having ground much closer and they don't have to penetrate the entirety of your dielectric substrate. So the losses are much smaller in a CPW line, and that's why we prefer to use CPW at larger frequencies versus microstrip because of lower losses. And it also has closed form approximation formulas to calculate the characteristic impedance on that as well. Here we have to also take into consideration the spacing between the center conductor and the ground plane. So now let's look at resistors. So if we want to design a resistor on a MMIC, then the resistors are made either using the active semiconductor layer beneath surface or a thin film resistive material alloys, or both type or have like metal contact pads on either side. So there are different types of resistors. One is a nichrome resistor. This resistor has resistivity around 20 to 50 ohms per square. Then there is tantalum nitride resistor, which can handle much larger current densities than nichrome resistors, and they maintain linear ohmic behavior under high stress. And there is also titanium tungsten silicate resistors, which have much larger resistivity as well, right? So there are subtle differences between which resistors we want to use, but essentially this is how it looks like. You have like your metal tracks, so you have your metal deposited, and then you have the metal pad, and then this is my center material that defines the resistivity. So this is a highly resistive material, so it can be a tan or a nichrome material, etc. In terms of capacitors, of course, we know that capacitor is defined as two metal layers sandwiching a dielectric material, right? So if we consider like a MMIC, then we have a substrate, and on that we have different types of metal and dielectric layers deposited. So usually for capacitors, there is a silicon nitride material deposition which acts as the dielectric for the capacitor, and this is a very thin layer, right? Then you also have silicon dioxide, that is also a material that is used to form the capacitor. Then there is a BCD polyimide which is much thicker and it has a higher extension as well. But BCD can then be used to essentially create much larger values of, much smaller values of capacitance. So there are different types of capacitors. One is called the interdigital capacitors, and here basically you have fringing capacitance between closely spaced metal fingers, and capacitance range is up to 1 picofarad, and this is stable against process variation and suitable for millimeter wave applications. But the most common type of capacitor we use is the metal insulator metal capacitor. So usually in a gas or GaN MMIC process, there will be two basic metal layers you will work with, and then there will be some sort of dielectric layer that will form the main capacitor. So this is the most commonly used gap in a MMIC process. Then if you look at inductors, how do we form inductors on a MMIC? We essentially pattern the metal in a spiral form to form the inductor. So when you do that, what essentially happens is the magnetic field on this center conductor start coupling with the magnetic field to the adjacent conductor, and that starts forming an inductive effect. And this is how the spiral inductor is formed on a MMIC process. So there are different types, but mainly we have spiral, single layer spirals, or in CMOS process, we also do stacked spirals. To achieve much larger values of spiral inductors, we can use multiple layers because in CMOS process, there are multiple metal layers available. So you can essentially have like smaller inductors stacked together to form one big inductor as well. Now, metal layers, because we work with different types of metal layers, we can also help improve the Q factor, and there are multiple ways to do that as well. But here you can see that this is an example that is shown over here. So this is a thinner line over here. The inductance of this is around 400 picohenry, whereas for this one it is around 240 picohenry. So essentially, as I mentioned before, any transmission line can be defined as a series L and a cap to ground. So the spiral inductor works the same way. It has a series L along the line, and then it has parasitic shunt cap to ground as well. So if we consider on a mimic, if we consider lumped elements versus distributed. So what are lumped elements? Lumped elements are components where your circuit parameters are assumed to be concentrated at a single point. Distributed are components where circuit parameters are distributed along the transmission line. So as I mentioned before, on a transmission line, you will usually have segmented sections of RC components together which form the entire transmission line. So that's the distributed element. Operating frequencies, lumped elements are much lower. Distributed elements is at higher frequencies. And then modeling approach for lumped is simple Ohm's law, Kirchhoff's laws. But for distributed, you need wave propagation equations and transmission line theory. And in lumped, losses are mainly due to resistive and dielectric losses, whereas in distributed elements, there is conductor, dielectric, and radiation effects as well. And then there are other differences, but the main thing we talk about is wavelength. So element dimensions are much smaller than wavelength, allowing ideal lump circuit behavior. But in distributed, element dimensions are comparable to wavelength. So you usually don't have a very ideal lump element behavior. You will have some sort of distributed behavior where your inductor will only be an inductor up to a certain frequency, which is the self-resonance frequency, beyond which it will not act as an inductor. So we have to keep that in mind as well. So this lump to distributed transition, when does it happen, occur? So transition frequency is defined as frequency where transmission line length becomes a significant fraction of your wavelength, typically approximated using the lambda by 20 rule. Okay, so in this example shown over here, there is this microstrip line which is in the 0.25 micron CMOS process. The structure is on top metal layer N5, so it has 5 metal layers. So N5 is the top and N1 is the lowest for ground, and it's separated by a silicon dioxide dielectric. Now, if we consider the width and length of this line, the transition frequency estimation using lambda by 20 rule is approximately 8.7 gigahertz. So using like an LC model analysis, approximately at 10 gigahertz based on like frequency dependent behavior. So we see that if we look at if we model it with like a simple series R inductance and shunt C and conductance model, we see that the inductance 1.1 to 1.2 nanohenry of the line remains fairly constant up to 10 gigahertz, and then capacitance is small initially, but it starts then increasing at higher frequencies because that gap to ground effect starts becoming very, very prominent. So that's why the model then starts becoming distributed and it no longer acts as an ideal inductor. Now for on-chip inductors, how do we value the, essentially calculate the value? You will calculate it using simple reactance is 2 pi FL, and or on-chip inductors, the number of turns, then the average diameter also allows you to calculate for the L value. The Q factor is very important. So Q factor is the quality factor of the passive circuit that you are designing, and for a simple inductor is defined by the reactance over the effective resistance on the inductor. Now, if we look at the printed inductors, so these are all like printed inductors, right? So we are talking about planar circuits here. Mimics, RFICs, they are all planar circuits. Planar meaning the metal layers deposited on them are thin enough to be called a planar, almost a 2.5D rather than 3D. So if we look at the equivalent model of the spiral, we see that it's not just an inductor, right? So it has inductance on the line, it has sheet resistance on the metal, then it has a CP value. So what is this CP? It's the parallel capacitance between the adjacent conductors. Then it has a COX value. So if this is on a CMOS substrate, then you have some sort of silicon oxide layer below it up to the ground metal. So that is the COX capacitance going from top metal to ground metal. And then you have ground metal to substrate capacitance and substrate resistance as well. So there is multiple layers, and that is how you model a printed inductor. So it's not just a simple L, but a combination of different passive elements. Okay, so now there can be different configurations, right? So you can use like a meander line, you can use rectangular spiral, circular spiral, octagonal spiral, etc. So there are different advantages and disadvantages to these. Usually we will use like a rectangular or octagonal circuit. A circular one is, it has the highest self-resonant frequency, but it's very difficult to do in layer. So for those reasons, we kind of stick with rectangular spiral. Okay. So let's then talk about stacked inductors. So as I mentioned before, that in a CMOS process, you have many metal layers to work with. Okay, so if you want to have a larger inductance value, you can reduce the amount of space it occupies by essentially stacking smaller inductance on different metal layers and forming a one big inductance value. But it's not as easy as it looks. So when you do that, you also start getting mutual inductance between the two, and there is mutual coupling happening as well. So that starts increasing your parasitic capacitance, and because it increases your parasitic capacitance, your self-resonant frequency drops. So you have to be aware that your self-resonant frequency will reduce if you do a stacked inductor. So this is an example in which they have like a CMOS process where they have substrate and then they have 6 metal layers on top. Okay, so they have designed this spiral using different metal layers. So if we look at the inductor that is designed only on a single layer, it has 4 turns. Number of turns is 4 on the spiral. We see that the self-resonant frequency is 50 gigahertz, and the maximum Q it has achieved is 15.2. Okay, but the inductance value is 1 nanometer. Then they use layers 6 and 5. Okay, so when they use 6 and 5, their self-resonant frequency dropped to 12.5. Why? Because now there is mutual coupling and the capacitance effect between the 2 layers. So it drops significantly. This also reduces the Q, but your inductance value increased because now you are essentially stacking 2 inductors together in series. So your inductance value is more. If we look at the last one, if you compare that to 2 layers, so you have metal 2 and metal 6. We see that the resonant frequency is little bit higher because metal 2 and metal 6 distance is larger, so the parasitic capacitance is little lower. But this enables the SRF to go little bit higher. If we consider 6, 4 and 2, 3 metal layers, we see that there's a lot of mutual coupling. Resonant frequency is very low, but the maximum inductance achieved is 10.1, which is quite high. Right? So depending on what you need for your design, you would basically design accordingly. So now your spiral has like a metal line, but there is also loss on that line as well. Right? So that is defined as a sheet resistance of the line. So based on the kind of metal you are using, you will also have loss on that. That affects your critical frequency on the line as well. So if we look at like conductor loss, we see that if your thickness of your conductor is more, then the resistivity is lower, and that enables in lower loss. So it's better to use a thicker substrate, a thicker metal versus thin. Then you have substrate loss, right? So if you have a metal in spiral, the substrate is going to result in like magnetic field loss and eddy current effect as well. So magnetic field penetration into the substrate results in eddy currents, that results in mutual coupling, that results in loss. So for lowest resistivity silicon, higher eddy current losses, high resistivity silicon, there is negligible eddy currents because the fields can't penetrate the substrate as much. So how do we improve like the Q of the inductor? There are different ways to do that. So one is like the trace layout itself, right? So you can do like different kinds of variable line weight, differential inductor, or you can add like thicker metal, or you can also do like pattern ground shield, which kind of breaks the ground fields. That helps in improving the Q of the spiral. So in terms of enhancement, if we see here, it is like different metal thickness outside versus inside. So narrow conductors for inner turns and hollow structures to reduce eddy currents, and then compact layout to minimize substrate penetration depth. So we see that these can also be used to improve the Q factor of the inductor. Then here an example is shown with like patterned ground shield. So we see that the spiral on a patterned ground shield versus silicon has much larger Q. So because that helps in kind of breaking up the eddy currents that are forming in the substrate, so that improves the Q factor as well. Now if we consider like a big capacitor, now the MIM cap is also using a transmission line. So it's basically two metal layers and there's a dielectric in between. So the way you would model it is you would have like the cap and then you would have an L and R, and then you would have the cap capacitor in between, and then you would have the substrate resistor and substrate capacitance to ground as well. So you would model it in that. Now for a MIM cap, if we consider metal insulator metal versus metal insulator metal insulator metal, we see that it has different values of inductance and sheet resistance. So considering what you are designing, what frequency you are designing at, all these things need to be taken into consideration. The main thing for a cap is to look at the SRF, and we see how like if it's below SRF, it acts as a cap. If the frequency is below the series resonant frequency versus parallel resonant frequency, it acts as an inductor, and then beyond which it just acts like a resistor. So it's very important to know where your frequencies lie for the specific design. Okay, so that concludes the passive design section. So next we will move on to like the active PA design considerations, right? So why this is very critical. So why is it critical? Because if we consider the transceiver systems, we see like on the base station specifically, or any other transceiver in a radar or any sort of sensor, we see that the transmit part consists of the PA as the last component before the antenna interface. And the PA is what consumes the maximum amount of power. So if we consider like macro base station versus pico base station, we see that PA is the only component taking up the bulk of the power in that base station. So it's very important that the PA you design be very energy efficient. Now, if we consider like different cellular standards, if we go from GSM, which was 2D to 3G to now 4G and 5G, we see that the efficiencies of the power amplifiers have been reducing and reducing. So they have gone from very high 50-60% for 2G standards to approximately 10 to 20% for current 4G, 5G standards. What is the reason for that? The reason being that for 2G, 3G, the bandwidth was much smaller and the signal complexity was much lower, whereas today's signals are much more complex, which don't allow for the PA efficiency to be much higher. So how can we improve the efficiency? We can improve using different upcoming semiconductor technologies such as gallium nitride. We can do low loss integrated packaging and use higher advanced PCB substrates as well. The other techniques we can utilize are the architecture of the PA. So we can use Doherty architecture, envelope tracking, or switch mode classes of operation on the PA. Now, if we consider the modern PA architectures which are being used for communication systems, specifically with high peak to average ratio signals, then they usually utilize more than one PA. So in Doherty, outphasing, envelope tracking, they all have more than one PA in the overall architecture, which allows for maximum efficiency and best performance. So if we look at the transceiver architecture by itself, we see that the PA is the final stage before the antenna, and the PA is not standard, also has a driver and a pre-driver as well. And the reason being that you cannot just have a PA with like an unlimited amount of gain. The gain of the PA is controlled because of stability and oscillation problems. So that's why we have to add driver and pre-driver stages as well. So if you look at the PA block, you usually will have like multiple chains of PAs lined up forming the driver and the final stage. Now in terms of the design, based on your spec, you can do the different types of designs shown over here. You can do a cascade, you can do, yes, there's a question.
Yeah, madam, I have a question. When we are designing these components,
Is there a question?
yeah, madam, can you hear me?
We can't hear you. You're asking.
Hello, hello.
I think you're muted.
Hello.
मोबाईल लाईट आहे ना तुम्ही कनेक्ट मोबाईल
Hello.
Hello. Madam, can you hear me?
You are muted if you are asking the question.
Hello. 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 Hello.
हॅलो हॅलो तर तुम्ही म्यूट ऑन केला आहे का नाही नाही अनम्यूट आहे
त्याला ऑफ करा.
हॅलो हॅलो मोबाईल ने कनेक्ट आहे का कोणी आहे का मोबाईल बोलू शकतो
इथे केलं तर तरी नाही होत.
हॅलो.
Hello.
हां चालेल चालला
Hello. 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 Hello.
Yes.
Yeah, madam, I have a question. Once we design this power components
Yeah,
like
ask
power.
please.
Yeah, madam, once we design these components like power amplifier for a specific frequency, what novelty we want to develop, because once they are designed, fabricated, they can be used for those specific applications. So, what new thing is required to design further? And how much will be the scope for designing these components?
We can do a Q&A session after the presentation if that's okay. I'll just
Okay,
continue
okay.
for now.
Okay, just to get some more insight, I just wanted to ask it in between. Okay, okay. Okay, madam, you can take it afterwards.
Okay, so you can do different topologies. So you can do like a cascade match, you can do parallel combining. This is all dependent on the technology you're using, the spec you have. Based on that, you will decide the architecture of it. So let's define what a PA is. So power amplifier is a nonlinear device. What does nonlinear mean? Meaning that at input, whatever frequency you give at the input, at the output, you would not just get that frequency, but you would get other frequencies at the output as well. And this is called harmonic distortion. So that's why it's called a nonlinear circuit. Now, it consumes the max DC power in the transmitter. If you want like a high efficiency PA, you usually operate it close to saturation, meaning that it is distorted at that point. Whereas at lower power levels, the operation of the PA is quite linear, right? But you don't get the best efficiency out of the device. So there is a compromise you need to always have between efficiency and linear. Now we already saw. Now we see that how the FET works. So this is just showing that you have reverse junction, and then once you start applying in a gate bias, your channel starts forming and the current starts flowing. So if we look at the IV characteristics over here, you will always bias your transistor at the Q point, right? So you would select a gate bias, drain bias, BB, and for the specific IDQ. So you would bias the gate accordingly. And then as you increase your RF signal drive, which is a sinusoidal waveform, you will see a dynamic swing of your voltage and current based on your RF signal you are providing. So that is known as a dynamic load line, which it covers the entirety of this graph. So based on wherever your Q point is, dependent on that, it decides how much is your total output's dynamic current swing going to be. So if we define the efficiency of the transistor, we define it as the output RF power over the DC power it has consumed. And the power added efficiency considers the RF input power as well. So it takes into account how much RF input power you have added. So this is the more critical parameter to define on efficiency. Then we also define like compression point, which we talk about where your gain is compressed by a specific dB value. Like for example, a 3 dB compression point means your gain is now 3 dB lower than your small signal gain, and how much will be your output power at that. So if we define the PA classes of operation, we have non-switch mode and switch mode. Non-switch mode going from class A, class AB, class B, class C, to switch mode going to more class F inverse, class D, class E. So if you look at like non-switch mode of operation, we have class A, class AB, class B, class C. So how are they defined? Basically, they are defined where you bias your transistor. And if you are biased at some specific levels, that defines your current conduction angle. So for basically how much of the cycle your current is going to conduct, and that defines your efficiency, right? So for class AB, class B, we see that my current doesn't conduct for the entire full wavelength, right? So it only conducts for some specific amount, meaning that my DC power consumption is reduced, so my efficiency goes up. But that also kind of drops my output power as well. So here, if we normalize my output power to class A level, we see that by the time we reach class B, class C, my output power is much more reduced. However, my efficiency is much higher because of lower DC power consumption. Now, if we consider harmonically terminated classes of operation, here we are talking about more class F inverse. Here, the harmonics that the device produces when it is saturated, such as second harmonic or third harmonic, they are terminated in specific load conditions. So, for example, in class F inverse, second harmonic load is terminated in an open circuit, and third harmonic load is terminated in a short circuit. What does this mean? This means that when my second harmonic frequency comes out of the device, it encounters an open circuit load. So it reflects back at that open circuit load, 180-degree out of phase, and then it mixes with my fundamental frequency, resulting in some sort of waveform shaping. Right? So when it does that waveform shaping, we see that for class F versus class F inverse, my fundamental current and voltage waveforms look like more like a switch mode, and this helps in increasing my efficiency quite a bit. Right? So if we look at like the power amplifier design itself, the PA design consists of multiple segments. So first, there are engineers who work on the die technology, which is semiconductor technology itself, like the physical semiconductor process. Then there are engineers who work on the DC and RF characterization of these devices which are fabricated to take measurements in order to do proper modeling of the device. Then a design engineer takes these models and does simulations and design circuits with the device. And once you have the circuit, then you will do package design and integrated PCB design, and then you will do a full system design using like a advanced architecture as well. So there are multiple layers to a PCB design, PA design. So how do we go about designing PAs? We first do the right device selection. So based on the specs you have, you would do the right device selection. Then you would do DC analysis, figure out where you want to bias your device. Then you do small signal analysis to look at small signal F parameters, gain, stability, input-output return loss. Then you do a load pull analysis. So load pull analysis is done to understand the exact load condition you want to provide the PA in order for the condition you want to achieve. So if it's like a max power condition or max efficiency condition at a specific operating condition, you would then look at the load pull and select the correct load for the device. Then based on that, you would do impedance matching networks for both output and input. Then you would do the circuit simulation, layout design, and EM proof simulation, and finally you would do the full analysis and business. So when we talk about device selection, we have to consider multiple things. One is frequency of operation. Second is power and gain spec, and what class of operation you are going to operate it. We have to understand that each technology has different power density, and based on the application we want to use and the cost associated with the application, we would select the optimum device technology that we want. It is very critical to also understand the frequency of operation and where the FT and Fmax of that technology falls. So let's say the FT of the technology is at 20 gigahertz and you want to design the PA at 18 gigahertz, it's not going to work because you won't have any gain, right? So you want to use the technology whose FT and Fmax is at least 4 to 5 times more than your fundamental frequency of operation. Then we consider small signal versus large signal. So what is small signal versus large signal? Small signal is called in linear regime, where your signal sinusoidal wave is small enough to be considered kind of like a DC level signal, where your dynamics response of the PA is not very different, right? So that is considered to be a small signal region. Whereas for large signal region, your output swing is going to be very high. So your dynamic current and voltage variation is going to be quite high. So that is known as large signal. So if you look at S parameters are for small signal linear operation and they do not hold for large signal operation. When we talk about large signal operation, we are talking about saturation level. So that's where we say large signal. So when we are talking about designing a power amplifier, we first determine the architecture, then we look at small signal design, and we look at large signal optimization as well. So for PS, what are the basic specs you need? You need frequency bandwidth, you need gain, you need to know the output power at some compression level, you need to know what is a fully saturated output power you want. You want to know what is the efficiency expected, input output return loss, temperature range, and linearity. So these are the specs you would usually get to design a PA. For a process selection criteria, it is based on the operating frequency and power optimization as well. So power density is usually defined as output power per unit size. So you would select the technology where you would get better power density for good amount of cost basis as well. And you would then do the power calculation of how much power you need versus what you have, and then do the proper architecture selection based on that. So you can have, like, let's say you want to use a transistor with uh, 200 micron gate peripheral. So you can either use like 4 cross 50 microns, or you can use a 2 cross 100 micron. So which one is better to use, right? So larger devices will give you higher output power, but then larger devices will also have lower gain because of more parasitics. So when we are thinking of power scaling, we have to consider that output power is proportional to devices. So the larger devices will give you more power, but larger devices will also have lower impedances, which will be harder to match to 50 ohms as well. And we have to also understand the parasitic effects for larger devices. So gate source capacitance will go up. It reduces the input impedance, and then source inductance provides negative feedback. There is phase errors along gate fingers if you use more number of gate fingers, etc. So those are the things we have to consider when we are considering what kind of device we want to use. So that's very important. Now, number of stages, right? So per stage, you should have the most amount of gain as possible. But it also depends on stability of the device as well. Since these devices, specifically GAN or gas, they have very high low frequency gain. It's important to consider how much gain can be used per stage, such that the amplifier doesn't become very unstable as well, right? So if you use fewer number of stages, your efficiency definitely will be more because there will be less amount of losses in your circuit. So it's best to use the minimum number of stages as much as possible. So optimize gain stages to minimize compression in early stages. Early stages are more driver centric, ensuring preceding stages provide enough power such that final stage is able to reach P1 dB, and balance between stage count, efficiency, and power conversion. Then we also do power combining. So power combining meaning techniques used to split and recombine the RF power between different amplification stages. We focus on like monolithic implementation, meaning that this is suitable for like mimics, and we have to consider insertion loss, size, bandwidth, and odd mode stability when we have power combining happening. So these are the things we need to consider. So when we talk about like parallel combining, we are talking about like multiple devices that are then connected together. So because they are connected at this common node here, it can induce some sort of odd mode instability in the devices. Then there is also like bus bar combining. where you have like a single low impedance line which basically combines the two PAs, and then there is like impedance matching happening after that. So if we look at this mimic over here, or the mimic on top, this is a great example. So we see that this is a shunt cap to ground. These are all vias. So this is a min cap with shunt to ground through a via. Then you have a series line which acts as a series L. Then you have a shunt line, shunt L, which is a line connected through a RF ground. So that's a shunt inductor, right? And this is my second stage FETs over here, and these are my first stage FETs. So similarly, in this, you can see that this is the DC bias pads, and then you have a bus bar here that is combining multiple devices too. And then you have like Wilkinson splitters here as well to split the power between different devices. So this is an example of power combining architectures. So when we are doing a PA design, it's very important to know the power budget. So what does power budget really mean? This is like the first step. When you have a spec, it's very essential to trace your power budget from your output power towards your input power. See how many stages you are going to use, how much gain each stage can approximately have, what kind of losses approximately will be present in your matching networks, and then based on that you calculate like the overall power gain and the power budget for your architecture. Then you do the small signal analysis once you have your architecture defined, right? So here you understand your max gain conditions, your input and output return losses, and then you look at stability. So you ensure that your device is unconditionally stable. If it is not unconditionally stable, you add stability networks such as in-band series RC to dampen the unwanted gain peaks. And then in your bias circuitry, you would add like bypass capacitors to remove low frequency oscillations as well. Right. So this just shows different types of gains that we define. So we look at the max available gain and how close we can come to our max available gain. And then when we look at stability criteria, we want our K value to be greater than 1 unconditional. Then we go to the large signal analysis. So as I mentioned before, for large signal, what happens is my dynamic voltage and current swing is much higher. Therefore, the amount of load conditions that can occur for a specific condition, such as having a specific power level with a specific frequency number at a specific compression, can vary quite a bit. And for this reason, we do a load pull analysis. So load pull is a technique which is used to optimize the impedance matching of a power amplifier for different conditions, such as output power, power added efficiency gain, or linearity. And the way it works is load impedance seen by the amplifier is varied systematically using a load tuner, and then you look at the performance metrics at each load conditions and plot those on a Smith chart. So here this is an example. So basically this is a power contour. So the central dot is showing my P1 dB max power, and then if I look at this next circle, all the impedances on that circle will have output power less than 1 dB lower than this point. So it will all be 19 dB. Then on all these impedances it will be 18 dB and so on and so forth. So that's how you read load pull contours. And you can plot load pull contours for like power, efficiency, linearity, gain, whatever, right? So it basically ensures that the PA operates at optimal performance, and it reduces power loss and improves the efficiency, and it helps in matching network design as well. So this is a basic like load pull setup where you have your amplifier, then you have your load tuner. So here I have like this shows like source tuner and load tuner, and in this calibration is very important. It has to be calibrated very correctly, and then essentially you start measuring your device in different load conditions and plotting the data. in the software. So this is basically a multi-harmonic load pull bench setup. So in my DUT, I have my die device, then I have bond wire and package, and I have a load pull fixture as well, which transitions this load impedance to 5 ohms. So this is some work that I had in Infineon. So I'm just showing an example of that. So when we look at like the measurements, we plot like max efficiency curves, max power curves, and based on that, we select the right impedance that we need for our specs, basically. So if we, so now once we have like the load that we want, so we determine that load, then what do we do is from that load, we essentially see that what is my device impedance. So if my load is like R plus JX, then that means my device output impedance is going to be R minus JX for max power transfer. So from that, we extract our RP CP values, which is basically the output resistance and output capacitance of the device over here. This is my current generator and output drain of my device. And from that, I then start designing outwards towards 50 ohms. So then I have my bond wire plus package and then my PCB going up to 50 ohms. And that's how I design my entire output matching. So when we design output matching network, we have to consider the bandwidth, the complexity, how much is it tunable, and how are we going to implement it. So these are some of the considerations to do when we do a matching network design. And of course, there are like narrowband matching network versus broadband matching networks. So this table is just showing the difference between the two. I'm not going to go too much into detail with this. And then you can do matching network design with lumped components, or you can use microstrip distributed lines as well. Based on the size of the circuit that you need, you would ideally choose your design components based on that. The lump components, if you use, like for example, if you use like a spiral inductor available in the market or a capacitor, the limitation is the SRF, so this has to be taken into picture. So that concludes my talk. So about my company, currently I do design consulting and training services in RF and microwave circuit design, power amplifier, module development, gas GaN mimics, any simulation support in ADS, AWR, HFSS, and then I have strong expertise in heterogeneous semiconductor technologies and EM simulations. I do custom training sessions and workshops as well. And the larger aim of the company is to develop millimeter wave chipsets for the Make in India campaign. So if any of you are interested to work on any collaborative projects together, or if you want to get some training services done for the students, don't hesitate to contact me. This is my contact, and I will also be sharing the slides with you as well. So that concludes my talk. Thank you so much for listening. I will take questions now.
Hello. Hello, madam.
So if there are any questions, please go ahead.
Madam, can you hear me? Hello. Hello.
I cannot hear you.
Hello. Hello. Madam, can you hear me? Hello. Hello.
Hello.
Yeah, I can hear you.
Madam, my question is, how much is the scope for this field of MMIC design? Because once we have designed circuit or the components for specific frequency and they are fabricated, then how many people are required to work in this area further? Is it not a saturated field?
Okay, you can mute, so I will talk. Yeah. So it is not at all a saturated field. In fact, this field is growing quite a bit, and it is growing because if you like, let's say you do, it's not that like you do a design at a certain frequency and then that's all. That's not how it works. Usually, like if you want to develop a product, it usually takes at least 2 to 3 tape out cycles to get the proper product out or proper like design out. And let's say you are doing like a X band PA design for one specific application. So you would like the designer would design the mimic, you would fabricate it, then you actually have to test it, make sure that it is working the way it's supposed to. Most likely it won't. If it's not working, then you have to figure out why it's not working and how are you going to improve the design. So that is a big cycle that happens. And then you also need to, once you test it, then you have to actually like integrate it into the system. That is also another challenge. So if it's not like if you have a mimic, it's just going to work. Integrating it in a system is another challenge that you have to work with, and you also need a lot of test engineers to do this work as well. And it's not like saturated because the system requirements keep getting more and more complex. So your design complexity also has to grow increasingly. So if you have designed like an expand PA today, maybe in a couple of years that system might get more complex, specs. So this PA will not work, and you will have to actually come up with a new architecture. So it's actually a growing field. I would not say it's like saturated. And because we are opening up newer and newer frequency bands for different kinds of applications, this field is actually growing quite a bit. I would say on global stage it is increasing. I don't know in India how it is. But even like, people in DRDO and ISRO, they design their own mimics constantly and they keep working to improve that.
Madam, how students should go ahead in this area to get a good career?
Yeah, so for students to have a good career in this, they actually have to do some real like tape out ready design projects. And then they would have opportunities. So right now in India, there are few IC companies that have started and they will grow as the years go by. So there are going to be a lot of opportunities in this area. And for students to like grow in this field, they should actually like do like training and projects specific to this area itself. Like they should actually like get access to PDKs, and I think universities in India, if you contact foundries such as Win Semiconductor or some other global foundries which have mimic processes, you can talk to them and see if they can share the PDKs with you so that the students can actually get to the opportunity to design in a proper process. So that will be a good opportunity for them.
Okay, so once they design some such mini project, can they apply, madam,
Yes.
companies after
Yes.
completion of their BTech?
yeah, BTech is hard. This field needs MTech at least. This field is not like BTech friendly because you don't study about this area as much in BTech. But if they are able to work on a project, a couple of projects in BTech level itself, then they can definitely apply for positions. Not maybe not as like a design engineer, but definitely as like test engineer, reliability engineer for sure.
Okay.
But like this field, like RF and microwave circuits, I think in BTech we are not taught much about this area. But this area is very important because all the current hardware that we use, everything uses RF frequencies. So even in BTech level, if students can work on some like hands-on projects pertaining to this area, they will learn a lot more. And even if they like learn simulation tools such as AWR, ADS, HFSS, they can definitely find positions in the industry. Yeah.
Madam, you said that MMIC is mainly used for industries like defense or aerospace, and for mobile phones, you said RFICs are designed.
Right.
So, if to create interest among students, because mobile phone which they use in their day-to-day life, so how to design mobile phone if that kind of approach needs to be developed
Yeah.
from teaching point of view.
Yeah. Yeah.
So
Yeah.
what we can do?
Yeah. So for RFICs, it is very difficult to get PDKs because they are all silicon, and usually silicon foundries they don't entertain like usually students much. You can ask and see, but I have done a RFIC MMIC month-long workshop in March this year where I made my own like PDK template and made the students design passive structures like passive filters in that template using EDS. So if you are interested in developing some curriculum like that, I can help you with that. Because I did it this year. I trained some students on this. So I designed our own like PDKs, something like an NPCC substrate and with multiple metal layers, and we did designs in that. So that's something that can also be done.
Yeah, so particularly mobile phone, if you use this title.
Yeah, but mobile phone is like, very fancy. Like this is not designing mobile phone, right? It's designing a chipset or maybe like a component inside the mobile phone. So yeah. So then that would make more sense.
Yes.
Yeah. Even like you can do like even front end design. So that would be more like designing more broader level mobile phone architecture. But these concepts are little advanced. So I don't know if like BTech students can do a complex project like this, but if you give like a much smaller project, like for example, designing like a filter bank or designing antennas for cell phones, then that is something that they can work. But if it is like more broader transceiver chain or something that is more broader and bigger project, that I don't know if BTech students will be able to accomplish because they need to know a lot more subject matter on that.
Yeah, so slowly standard can be increased, na?
Yes.
Yeah, I will be in touch with you, madam, regarding this.
Yeah, sure. Yeah, I mean, I create workshops and materials. So I had a very successful workshops this year on RFIC and MICs, and then even at a couple of IITs, I gave very good workshops. So if you are interested in developing like a course on this, I can help you with that. Or like a short course.
Yeah, okay, madam.
Yeah. Any other questions? If there's no further questions, then I will conclude the workshop. Thank you so much for attending. I will be sharing the slides with Mr. Anand Deshmukh, and then he can distribute it. But yeah, otherwise, thank you so much for having me. I appreciate it. And if any questions anybody has, please reach out to me. My email will be there in the slides, so you can reach out for sure. So thank you.
Yeah.
We can't hear you, sir.
Yeah, thank you very much, madam. Hello? Hello?
Hello?
Yeah, thank you, madam, from on behalf of Cummins College of Engineering, Electronics and Telecommunication Department.
Hello?
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 Yeah, madam, we are thankful to you for delivering this session.
Delivering this session
Cummins College of
on behalf
Engineering,
of Cummins College of Engineering, Nagpur, and particularly Electronics and Telecommunication Department, and this
ATAL FDP.
ATAL FDP.
Yeah, thank you so much.
Yeah, we were in need of
some person who is from outside India because lot of work takes place outside India.
In
In this team of our ATAL FDP. So we got a person in form of you.
And
So we are really thankful to you for taking this session.
And
Yes,
we
yes,
will be,
my pleasure.
we will be in touch with you.
Thank you so much, Mr. Deshkar.
Thank you, madam.
Thank you, madam.
Thank you. Bye.
End the call for everyone. Live